and it's indeed my pleasure to welcome you to the 59th Annual Research Lecture. I'd like to recognize Professor Amy Wohlert in here from the President's office, right there. Also Katie Richardson from Senator Heinrich's office, and Judge Harris Hart's U.S. Court of Appeal 10th Circuit, people from outside the university who are with us tonight to celebrate our research lecture. I also would like to thank the members of the UNM faculty and research community for joining us this evening as we honor an eminent scholar from among our ranks. I would also like to thank and give a warm welcome to our guests from the broader community joining us for this very, very special event. We come together this evening to celebrate and honor the significant achievements of Professor Ivan Deutche. I didn't memorize it. Of UNM's Department of Physics and Astronomy. I knew that's where you were from. The Annual Research Lecture Award is a long-standing UNM tradition, 59 years, that brings us together each year to recognize the diverse contributions of our faculty. It is the highest honor the UNM faculty can bestow upon a colleague in recognition of their research and creative works. Through this lecture, we are privileged to get a glimpse of the talent that is found in a diverse array of fields ranging from the arts and humanities to medicine, the sciences, and engineering. UNM places a high value on research and is proud of its designation as a very high research university. Last year, UNM faculty researchers generated over $200 million in external funding in support of the research mission. This funding represents but one aspect of our faculty's commitment to research and their dedication to excellence. Perhaps a greater testament is found in the students and colleagues they mentor in their respective fields. In this context, we see the necessary skills for scholarship and creativity translated from one generation to the next. At its very core, our faculty's research and creative works serve as the drivers that will continue to foster innovation at UNM well into the 21st century. We are fortunate to have faculty members like Professor Deutche tonight who serve as master practitioners and models of excellence in the classroom, in the laboratory, and on stage. I would personally like to thank Professor Deutche for his contributions and his leadership in this effort, and I'm looking forward to his lecture entitled Breaking Heisenberg, Controlling the Quantum World. It's fitting that we have also a fellow faculty member and eminent scholar in his own right to introduce Professor Deutche this evening. Professor Caves is a distinguished professor from the UNM Department of Physics and Astronomy, and he serves as the director of the Center for Quantum Information and Control. Following Professor Deutsche's lecture, there will be a brief question and answer period preceded by the presentation of the award citation by Vice Provost for Research, Dr. Mike Dewar, and followed by a reception in the STEM room. Please join me in welcoming Professor Caves. Thank you.
All right. Ivan Deutche is a professor of physics and astronomy. I'm going to stop for a second and just take that title apart for you. First, the astronomy in the title is purely honorific. Don't ask him questions about astronomy. I think I'm not insulting him by saying he doesn't know anything about astronomy. Ivan's a physicist. Professor, what does that mean? What do we do with our time? Well, our job description is that we do teaching, service, and research. Teaching. We're all familiar with classroom teaching. I'll say a little bit more about Ivan's classroom teaching in a minute. But in addition to classroom teaching, we work alongside undergraduate and graduate researchers, students that we work with on research in a role that might be called apprentice teaching. That is, we train them in research by doing research with them. Ivan's research is very much of that character. Service. We run our departments, and we actually pitch in and help run the university. And then research. We investigate the boundaries of the known, so we can push back the boundaries of the known into the unknown. So that's our job, and let's return now to that, what Ivan does. He's a professor of physics and astronomy. He's actually a physicist. In fact, he's a theoretical physicist whose interests have taken him in the direction of working in a new field called quantum information science. So I'm going to step back a little bit and say something about physicist and quantum information science. Ivan is, as I said, a physicist. He's a theoretical physicist. And what does that mean? Well, in physics, more than a century ago, we realized that the workload and the expertise in our discipline was sufficiently specialized and complex that we divided the discipline in two. And nearly everybody in physics is either a theoretical physicist or an experimental physicist. Theoretical physicists investigate the consequences of the physical laws, and experimental physicists go out and actually test those consequences. So remember, Ivan's a theoretical physicist. You're not going to see pictures of him working in the lab, although you might see some pictures of laboratories in his talk because he works closely with experimental physicists. Quantum information science, what's that? Well, I think we all have at least some idea that there's something weird and wonderful about quantum mechanics, that from the popular press or from popular books. But what has been discovered in the last 3 decades is that we can use those weird and wonderful properties to do useful things, to do things, in fact, that cannot be done in the world of our ordinary experience. Ivan works in that field. His particular specialty is called quantum control, which is studying how to make quantum systems, systems in the world of the very small, do what we want instead of what comes naturally. So now I'm going to have to refer to my notes and see where oh yeah, I know where I am next. When I began putting together Ivan's nomination for this award, I wasn't sure that he would win. And why is that? Is that because he's not a good researcher? No. No, he's an outstanding researcher. The reason is he's too good at the other aspects of the job. He is an outstanding teacher in the classroom, one of the best in our department. He serves as the associate chair for graduate affairs in our department. And with me, he runs the Center for Quantum Information and Control. He just doesn't get to call himself director. So he's outstanding in all aspects of being a faculty member. Giving him the university's highest research award is a little bit like taking the most valuable player in Major League Baseball and giving them the award for highest on-base percentage. He's good at everything about being a faculty member, not just research. But, you know, we'll take what we get. This is a terrific award, and I'm very pleased that Ivan has gotten it. The research itself, Ivan will tell you about that. So I'm going to close by making just a couple of points. The first, Ivan does his research in collaboration with a team of undergraduate and graduate researchers. Remember that apprentice teaching? This is it. Research in an American university is education. We train the next generation of workers in the sciences. Ivan has supervised 13 PhD dissertations with 2 others nearly cooked, 2 MS theses and 4 undergraduate honors theses. And these people staff the top level institutions in the world. So that's the first point. Ivan does his research in collaboration with his students and his postdocs. The second is, what about the research? What about the impact of his research? Well, here I'm just going to appeal to authority. I'm going to appeal to authority by quoting one of the letters submitted in support of Ivan's nomination for this award. And I'm going to quote William Phillips, who is an experimental physicist at the University of Maryland and at the National Institute for Science and Standards and Technology in Gaithersburg, Maryland. Bill is a distinguished university professor at Maryland. He received the 1998 Nobel Prize in Physics for his work on cooling and trapping of atoms, and this is what he says about Ivan. Ivan's influence on quantum information science cannot be overstated. My own group's activities in quantum information, along with those of other groups around the world, follow directions that Ivan set. Ivan is the ideal theorist. He has the big ideas that open new research directions, and he provides the detailed calculations that allow experimentalists to make use of his ideas. Pretty good endorsement. So, I know I've been embarrassing Ivan, and I know you came to hear him anyway, so I'm going to stop. Here he is.
Boy, gee, talk about, it's like more than a bar mitzvah here. All right, okay, well, thanks everyone for being here. It's a great pleasure to see the big community of friends and colleagues and neighbors and students. And so let's hope we'll have some fun tonight sharing the experience here. But it is coming up on finals week, and you know, I am a professor, Charles, so we're going to have a little test. Now, as you also know, many of you know, I recycle my homeworks and tests, so if you've seen this test before, don't shout out the answer, okay? So, here we're going to start. Does anyone have an idea what this is? How about this one? Quiz show. This one is game show, okay? So, why is it that this one you could guess, but this one was pretty much impossible?
Too many vowels.
Yeah, I mean, vowels aren't a lot of information, right? This is a lot of information. And this, because we know something about the English language. We know how often we expect to see Z's and Q's. And based on what we know, we make predictions about what the answer is. And so this is the first point. As Carl mentioned, we're working on the problem of quantum information. So the first question is, what is information? And the answer is, information is about what we know, okay? And what we do as logical beings is make deductions, we make predictions about the world based on our prior information. And the way in which we do that, if we're active, the language of logic is probability. Now, I know all of you from different backgrounds, but even those of you who aren't scientists, I know social scientists, and we have to do statistics, right? So probability is the language of logic. And we might argue, we have to say, well, what's my chance of seeing a particular outcome? I think logically. I say, if I saw, if some data happened, if data 1 happened, then there's some chance that this guess is true, and then, but I have to weight that by the probability that data 1 happened. So I have to think if, then, do some probabilistic thinking, logic. Okay, now we all know that in the modern world, our modern economy, our modern life is all about processing that information. And there are lots of ways that information is processed. That information is communicated from one to another. Sometimes we have to hide that. I don't know how good we are. The NSA is out there. Maybe they're here now. I don't know. I'm sure they are. And we take input. We do algorithms. We make computations based on the input. Okay. So as we know that information today, we think about it in the digital world. And when we process that information, we digitize that into simple answers, yes or no, true or false, on or off. And we process that through some set of circuits that for example, turn true into false. They say not. If not true, then false. If not false, then true. And the logic proceeds. This is done on machines. We all have our computers, our iPhones, what have you. And as we know, these chips are shrinking more and more. I mean, this iPhone has, probably was much more powerful than, going ahead here. Much more powerful than the computer I'm sure I did my PhD thesis on. And that's due to the fact that we're shrinking these, the components on these chips to smaller and smaller and smaller levels. And then when they're very close together, we can do very fast computations. And there's something called Moore's Law, which was just sort of noticed by Gordon Moore, who was the CEO of Intel, that there's this kind of exponential scaling of the way in which the chips are shrinking so that every 2 years you get twice as many components on these chips. And if you just took that literally, then eventually, not too far in the distant future, if we keep shrinking and shrinking and shrinking and shrinking and shrinking, eventually, and according to this extrapolation, in the year 2050 something, we'll get, you can't, I guess it's bad resolution, but that says a hydrogen atom. Okay? So if we keep shrinking this, eventually we're going to get down to some scale where you might think this doesn't really act like your normal kind of machine. It's on the level of an individual atom. Something weird is going to happen at that level. All right, so now what happens when Moore's Law hits physics? Well, now we got to introduce our first character of the show. We got to meet Heisenberg, but actually, that's not Heisenberg. That's Heisenberg. And according to the World Authority Wikipedia, this is what Heisenberg is known for. Heisenberg was a German theoretical physics and one of the key creators of quantum mechanics. And in 1927, he published his uncertainty principle, upon which he built his philosophy for which he is best known. So he's not known for making math, he's known for quantum mechanics. All right, so what is this uncertainty business? What is it that happens when we start shrinking down to this level of the atomic and subatomic? All right. Well, to do that, what we like to do as theoretical physicists once in a while is do a kind of thought experiment. So we're not doing experiment, we'll do a little thought experiment here. Okay, and here's the experiment. What I'm going to do is I'm going to send one of these single subatomic particles, a particle of light that we call a photon, and we're going to send it on this piece of glass. Okay, this piece of glass that we call a beam splitter, which is what we call a 50-50 beam splitter because it's like a fair coin. With half the chance, this photon can transmit through this piece of glass and hit this detector, and the detector's like a Geiger counter and it'll go click. And there's a 50% chance that it will be reflected and hit this. So that's what's going to happen. Either it does that or it does that, half the time. Absolutely never, ever, ever for this single source do these both go click at the same time. This is an indivisible particle. It can't be divided. It clicks one place or another. Okay? All right, but now we're going to make life a little bit more interesting. And we're going to, there are two possible paths, but we're going to set up beyond this single beam splitter, we're going to have these two mirrors here, and then another beam splitter. So either the photon can go along path 1, or it can go along path 2. So now I ask you, what's the chance, just from logic, remember, if this, then that, that either this detector will go click or that one, right? Because there's a 50% chance it can go here, and then when it hits that, there's a 50% chance it can go through or go click, right? So that's a quarter of the time. And then a quarter of the time it could do the same thing. So again, you would expect 50-50. Half of the time it goes here, or half of the time it goes here. But in fact, that's not what happens. 100% of the time, all the time, this detector goes click. And it never, ever goes click like that. And that's just illogical. I mean, it just doesn't make any sense. Because we just said, you know, if it went this way, then 50% of the time it go one to the other. So what's going on? This is the most basic example of what we call quantum weirdness. This is what is called quantum interference. There are two logical alternatives, and those two alternatives interfere with one another in an illogical way, in a way that we just can't even, we know how to write a mathematical equation that will predict this, but it just doesn't make sense. And in some sense, what we say, even though this particle only clicked one way or the other, it kind of went both ways and interfered with itself. It's kind of in both places at the same time. So the lesson here is that quantum mechanics can defy logic. Okay, but then you say, come on, Deutche, give me a break. I'm just going to take a look. I'm going to sneak in with a little detector that's going to see which path the photon took, because it only went one way. So I'm going to put this little detector in here, this crystal, which will light up if the photon goes through it without absorbing it. Okay, so it's going to peek and say, which way did it go? And when it does that, we know that the photon took this path. And when you do that, what you find is half the time it goes one way and half the time it goes the other, which is crazy. But that's the way it is. Just the act of knowing which path the photon took changes the alternatives that could have been. And because this is the only alternative that could have been, then there's a 50-50 chance. It's only when those two alternatives are in principle indistinguishable. We couldn't know, do we get this quantum interference between the two? All right? Crazy. All right, so we can't simultaneously know which path the photon took and at the same time see interference between those paths. So this is an encapsulation of the kind of the Heisenberg uncertainty principle. And it's kind of the way we grew up, people like Carl and me, learning about quantum mechanics. Quantum mechanics was kind of like a nag. This is Carl's explanation. I think it's pretty good. It's kind of like, it seems like a paler version of pristine Newtonian physics, the clockwork physics where everything is precise. It seems like, you know, there's this imprecision. It goes both ways. We don't know. And it seems like it kind of gets in the way of knowing. However, we want to go in a different perspective here. We're going to look at this from a different perspective. Quantum mechanics is the enabler, okay? Quantum mechanics is not the nag. Quantum mechanics opens the door. It opens the door to do things that were just not possible in the classical world and the world of Newton and precision. And what my research has been about, and what I'm going to tell you about, is about how we can use this to process information in completely different ways than we could on these devices like our iPhones. Let me grab a quick drink. All right, so we're going to have logic. The thing that's different in the quantum world is, as we said, we had this notion of digital. Yes and no, true or false, 0 and 1. But in the same way that the photon can take both paths, we can have true and false at the same time. We can exist in this limbo land, what we call quantum maybe land, which is in between. And it's kind of represented on this. What we like to do in theoretical physics is we like to abstract these concepts, give them a kind of geometric meaning. So where 0 is, say, at the North Pole, 1 is at the South Pole, and everything on the equator is an equal possibility of true and false at the same time. However, there's this weird thing. There's something like true plus false and true minus false, whatever the heck that means. But what I'm telling you is that this quantum state is as different as this one as true is from false. 0 plus 1 is completely the opposite of 0 minus 1, okay? And there's all these things in between, a little bit 0, a little bit 1, all of this, all the continuum around this circle. And there's a way, I'll not get into it, that we can represent this in an algebraic formulation that we use in terms of predicting the probabilities that we'll see when we actually look at this photon in the same way that when we asked it, did you go this way or that? It only told us one answer. If I look at this bit and I ask you, are you true or are you false? It never says, maybe. It tells me 0. It says true or false, just with some probability of that to happen. So we can do the kind of logic. If we're going to have quantum bits, those are what these are called, qubits, then we have quantum logic. And so we can take the North Pole to the South Pole and the South Pole to North Pole. That's fine. That's the not. That's what we said turned true into false. But there's more in the quantum world. There's, we could take this weird state to its opposite. And more. We could do the square root of not. Okay? Now you remember the square root is this thing that you do twice. It's like squaring it. So the square root of not takes true into maybe and false into the opposite maybe. And if you do it twice, you go from false to maybe to true. That's why we call it the square root of not. So there's a whole different kind of logical way of thinking. We have something kind of in between, some limbo world, taking our flatlanders and moving them out into a different dimension of sorts. So, for example, we can do, with this quantum logic, we can put gates together. We can take a situation where we say started with a quantum state which we had both true, we do the square root of not, we end up in maybe, and then we do some kind of conditional logic which flips this bit conditioned on that one. And we end up with two possible outcomes. So we end up with, depending on its algorithm, we ended up with the register being both 0 or both 1. So in some sense, this computer did two calculations at once. It was able to both compute what happened if the input were 0, or it computed what the input were 1. It does two calculations at the same time, in the same way that the photon went through two paths at the same time. All right, now this has been heady stuff, so we need a commercial break. And I'm a child of the 70s, and this was one of my favorite commercials, so let's get it. So this was, you know, the idea of going viral with your shampoo before there was Facebook. And the idea is they wanted people to buy Fabergé shampoo with their Farrah Fawcett hair, which mine look close. Well, you'll see later. And so this was the idea of getting all your friends to use the same product of you will very quickly propagate and have lots and lots and lots of people using your shampoo. So if, you know, they tell 2 friends, that's 2 times 2, and then they each tell 2 independent new friends, that's 2 times 2 times 2, that's 8, etc., and so on, and so on, and so on. And just with 10 people doing that, by that time 1,000 plus people are using the shampoo. And if 100 people did that, by that time, that's a nonillion friends, okay? That's more friends than there are than stars in the universe, okay? So clearly, you're not, and I do know, that I had to look up, I did, because I don't know a lot about astrology. I'm sorry. Trish, I apologize, I'm sorry. But this sort of gives you the flavor of why a quantum computer in principle could be so powerful. Because what we're doing, if suppose we have n qubits, n of these bits, okay, say there are 100 of them. Well, that means there are these nonillion different possible strings of 0 and 1. Now, in a classical computer, you have one of those, that's fine. But in a quantum computer, they all can exist simultaneously. You can have this superposition of all possible strings of the register of your computer at the same time. And it's like this giant interferometer, but with a nonillion different paths that can interfere and do these parallel computations. And you can kind of imagine that would be a very powerful thing to be able to do. So the question is, where is my quantum computer now? Why don't I have a quantum computer now? Because it looks so awesome. Well, the problem is, as I said, if anything can tell which path the photon took, the whole thing falls apart. We don't have all those combinations at the same time. We just have one of them, and then who cares? I just have one calculation. And there are a lot of different paths, computational paths as we call them, that could have happened. And because of that, any little noise in the world, any tiny little bit of disturbance will distinguish which of those paths happened, and it all goes to heck. So that gives us something to do. It's job insurance for a while. Okay, and this is reminiscent of a very famous paradox. One of the kings, the founding fathers of quantum mechanics, Erwin Schrödinger, contemporary of Heisenberg, who just took the conceptual aspects of quantum mechanics to its sort of absurdum conclusion. If the way in which the natural world works includes this possibility of dual alternatives where 2 things can happen at once, could we engineer a situation where his cat could be both alive and dead at the same time? Where he imagined, you know, this quantum event, a nuclear disintegration, would cause a hammer to hit a poison vial, and the poor kitty, I don't know why we don't have Schrödinger's dog, but it's Schrödinger's cat, would unfortunately be poisoned. But there's a 50-50 chance of that happening, that disintegration of that nucleus. And that exists in quantum superposition. So then you would have this correlated state where either the nucleus didn't decay and the cat is meow, or, you know, the nucleus does decay and the cat is like that. So the question is, it's a kind of it's an important thought experiment. At what point, where does the quantum world end and what we call the classical world begin? And how do we understand this? But the truth of the matter is that we never see this kind of macroscopic superposition state in the real world. And that macroscopic superposition, that simultaneity of dead and alive, would have to be seen through some kind of interference, some kind of possibility of interfering these two possibilities. And it just is very difficult. It doesn't happen in the natural world for the reasons that I described, that any little disturbance that distinguishes these two makes one of these two, in some sense, the choice that happened. So what our goal is, and what my research is involved in, is how do we take this microscopic superpositions, these microscopic realm of possibilities, and try to engineer them, try to bring them into our macroscopic world. And to do that, well, we need something, firstly. All right, time for some control. We need a test bed for a place, a natural system that we can then experiment with and engineer in order to move it from this realm of the atomic and subatomic more towards the macroscopic. And the platform that I've explored for a number of years is the platform of what are called ultra-cold atoms. These are atoms, this technology, this idea was developed by Bill Phillips, the Nobel Prize winner that Carl mentioned in his introduction, who was my postdoc advisor. And this is a picture of some cold atoms in a big thermos, basically. It's a big vacuum tube. And that little blob there, those yellowish things, are sodium atoms. They're like those horrible sodium lamps that you remember you drive down the street and they were ugly, ugly lamps. They were sodium lamps, and they shine this color. Now, these atoms are ultra cold. They're so cold, they're almost at the absolute minimum temperature possible, where all motion stops. The temperature on the surface of the sun is 200 times that in absolute temperature than the Earth, but these are 300 or 30 million times colder than room temperature. So that's pretty damn cold. And when they're that cold, we can then manipulate individual atoms. We can hold on to an atom. And we looked at trapping these atoms, and was discovered just around the time I was a postdoc that these atoms were so cold that they would fall into these little kind of egg carton-y type crates where individual atoms are arranged in a lattice that's created by light. And this is our platform that we're going to look at and use to try to manipulate, to try to control the quantum world, and to try to implement these concepts of quantum information science. Now, the work that I've done, I really must share a good deal of credit for it, has been in close collaboration with a good friend and colleague, Paul Jessen, from the Optical Sciences Center, now the College of Optical Science in Tucson. Paul was also a student with Bill Phillips, and we met back then. And when I moved to Albuquerque, he was in Tucson. That was kind of like next door here in the West. And we started to work together. This is back in 1996. And we realized that optical lattices, this idea of crystals of cold atom, were a kind of natural playground for us to explore, a kind of tinker toys for us to explore what was going on in this quantum world. And what motivated us, partly what was going on in other fields. So around that time, there was a lot of excitement about what was going on with trapped charged atoms, what are called ions. And Dave Wineland, who a couple of years ago won the Nobel Prize, but back in 1996, he was just Dave Wineland, was exploring this idea that if you could really have individual atoms and you can point laser beams at them and manipulate them, you can do quantum magic with them. And so we wanted to do what was being done with these few, 8 ions with 1 million atoms in this lattice. So we'd have a lot more, all these different paths to explore. Okay, so quantum control was what we were doing, and Paul and I wrote this paper back in 1998 where we were exploring optical lattices as this platform for doing quantum manipulations. And one of our first works on this was what we called in that paper a Schrodinger cat, but it was really should be called a Schrodinger embryo or something like that. It was just a tiny little atom which was in this superposition state of being in two places at the same time. That atom could be over here in this egg carton or over there in that egg carton. And we can manipulate that. And we understood what would the signatures of that be. What would the experiment do to show that indeed this atom was in two places at the same time, or potentially. But more importantly was the idea that the quantum properties of the optical lattice naturally align themselves with the possibility of doing this kind of quantum logic, where you would flip one bit conditional on the state of another. And so what we looked at was how would you take these egg crates and do kind of chemistry with them. Take two individual atoms and put them together. They're just two atoms, but there's many, 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 many copies of them. This is not like the chemistry where you just pour liquid in and then the natural processes. These were individual atoms that we can move around and try to click them together and have them do logic. And that work was really the basis of a big opening in the field. One of the things that we researchers take pride in is the fact that what we do is part of a big community and that there is influence that comes and goes in different directions. And the idea of the optical lattice has really grown over these decades, in which people have thought about these crystals of light as ways of simulating the nature of matter itself, or for making the most precise clocks in the world, the uber precise GPS that we might have in the future. And so we were a part of this community that's grown since then. Okay, now there is no clock in here, and I want to see what time we got. Okay. I'm just going to give you just a little bit more of a taste. We won't do much more about the kind of thing that we've done since then. So what we really want to do with this platform is develop the mechanisms we need to process information in this way. We want to be able to design protocols that will generate these arbitrary superposition states and be able to do arbitrary dynamical evolution on the system and do arbitrary measurements on this system. This is what we call quantum control. And our platform for doing that are these atoms. These atoms are made up of electrons and nuclei, and we want to manipulate these individual atoms. And you can think about this atom as a kind of spinning top. So the atom we use is cesium. It's a big, fat, chunky atom. It's got lots of nuclei. It's got lots of electrons. It's out there on the periodic table. And it enables us to explore these kinds of quantum superpositions in which we have many, many different alternatives. In this case, 16 different possibilities that we all want to make in superposition at the same time. The way we do it, although I'm not a theorist, I'm not an experimentalist, I play one on TV sometimes, and so here's the experiment. This is the experiment out of Paul's lab. And we shine radio waves and microwaves on these atoms in order to control them in very precise ways. So I'm going to show you a little movie just to give you a flavor of the kind of thing that we do. We want to make this crazy superposition state, which is shown abstractly, whatever the heck this means, some ball with some bright spots and dark spots. And our goal is to start with some well-defined spin that's pointing in some direction and have it end up in some particular superposition state. Well, we design a control waveform which stretches out this quantum state and morphs it into exactly what we want, something that would never happen naturally in nature. But by understanding how we can drive the system, force it with these fields, we can create these superposition states. Okay, now we have these superposition states, we want to measure them. And this is the last thing I'm going to tell you about. Now, one way you want to measure something complicated is to do what's called tomography. This is like a CT scan. How does a CT scan work? Well, what you're doing is you're taking pictures from lots of different angles, and you're doing a projection onto a two-dimensional plane of what this three-dimensional object is. And then with some computer algorithm, you put together back what was this three-dimensional object that looked like that. So that's why this poor soul has to spin around. Well, actually, it's the magnets that spin around them. It would get pretty sick in there otherwise. All right, so what we want to do is quantum tomography. What we want to do is spin our quantum state around in 16 dimensions, take pictures of it along all 16 dimensions, whatever the heck that means, and then have an algorithm that reconstructs and says, what was this thing we took a picture of? So that's what we do. We shine, we get some signal, and we're going to feed it into computer. So I'm going to show you just an example of the kind of collaborative work that I've done on this with my colleagues. So what I'm going to show you in this little movie, here is a quantum state, whatever, it's just shown as a bunch of bars here. It's 16 by 16. And if we measured it along these 16 dimensions, then the claim is that there's these wiggles, okay? They go up and down. So now we have an algorithm that says if we see these wiggles, this was the state to produce it, and here's the data. I'm very proud of this because this is one of our great predictions. The data, this is not with any fit, the data lies exactly on top. This is not, the gray was what we predicted we would see. The red is what the data was. And it shows that, I mean, this is a long collaborative effort going back and forth between theory and experiment that the system can be controlled so well that we know exactly what every tiny little wiggle is going to be. And based on that, we can infer what was the quantum state that made that. All right, it's been a long evening. Let me just conclude by echoing some of the sentiments that Carl raised in his introduction. I've been honored to work with a number of wonderful people, and one of the great pleasures about being a professor is working with students. And in particular, the nature of graduate research itself is that that is what graduate education is about. And I have had a number of PhD students, many of whom are here in the audience. These are students who have graduated in the past. These are my students currently. And so a message I want to bring across here is that often we think about research and teaching as separate enterprises. But in fact, really, they are intertwined and one of the same. Everything that we learn in the classroom, we bring into the laboratory. What we take from the laboratory, we bring into the classroom. The nature of higher education is that the knowledge producers are the knowledge distributors, so that when I'm going into the classroom, I get to enjoy talking about the passion of what I do to everyone. And that happens in the classroom, and it happens in the laboratory and the virtual laboratory. I've also been blessed to have many wonderful mentors. This is vintage 1989. That's not quite my Farrah Fawcett hair, but it's close. My mentor, Professor Raymond Chow, is here in the audience, and he really instilled in me a tremendous amount of creativity and inspiration. Bill Phillips, we heard about, was my PhD mentor. Ray actually took me first to Santa Fe. This is vintage 1991. That's at the Plaza. Yes, I did have a lot more hair back then. And at that meeting, I got to interact with another gentleman, one Carlton M. Caves, who has been a tremendous mentor and friend to me for many years, and I've been very lucky to have all of these mentors helping me and pass on this to future generations. So thank you very much. So now we have some questions. Yes, a question.
Can you explain briefly and in a way that I can understand, but how the laser cools down atoms?
How do lasers cool down? That's a good point. I didn't actually tell you that. So, yeah, lasers usually heat, right? So how in the world is a laser going to cool? Well, the way the laser cools is, you can think about it this way. Think about the atom as a big, heavy rolling bowling ball, okay? And because it's rolling, it's got some temperature. It's got some energy. And the bowling ball, say, is rolling towards me. Now, I'm going to have this ping pong machine gun, right? And those ping pongs are scattering, they're bouncing off the bowling ball. And if enough of those ping pongs recoil against the bowling ball is going to stop. And the bowling ball is going to cool off. The bowling ball is going to have less motion. So now, why doesn't that always happen? Well, that's because most of the time, the ping pongs don't bounce off. They get absorbed into the bowling ball, and that heats it up. But an atom spits it out quick. And because of that, if you can shoot enough ping pong balls at the bowling ball, it'll stop. And that's how laser cooling works, basically. Yeah.
So you describe looking at a three-dimensional world as measuring it as
Right.
a projection into a two-dimensional plane.
Yes.
In looking at these multiple simultaneous quantum states,
Yes.
are we potentially looking at a projection of an n-dimensional object or system projected into our own three-dimensional world and method of measuring?
Right. Okay. So let me repeat the question for the camera, which is, how should we view this notion of tomography, where we project it onto a plane, a three-dimensional image? Is there a kind of way in which we're projecting this quantum system that exists in multi-dimensional space onto our natural three-dimensional world? The answer is not quite. The reason is, and there's this big, big abstraction. When I talk about the term dimension, it's a mathematical construct. This is not six-dimensional space like string theory, where we say there's this 11-dimensional world. This is a notion that we use a mathematical abstraction. So when I say 16 dimensions, It's not 16 spatial dimensions. It's a kind of construct, meaning the 16 different alternatives, the 16 alternative possibilities that could have happened. So it's not a projection in the usual sense of three-dimensional space. It's an abstraction. Yeah, back there on the left. The very first slide. Okay. Yeah, let's go there. I don't need to control the quantum world anymore, so. This guy. Is this the one? Oh, well, so that you have to make the glass. I mean, it doesn't always happen that way. You have to buy the right piece of glass from the optic shop that from Thor Labs that is a 50-50 beam splitter that is calibrated that will reflect half the light and transmit half of it. It's like a window. When you're looking at the window, if it's very bright outside, you see a reflection of yourself in the mirror, but if in the glass. But on the other side, people can see you. So some of the light goes through the glass, and some of the light gets reflected. But the single photon is weird, because the single photon has a 50% probability, a potentiality, a possibility of transmitting, and a possibility of reflecting. But it only, when you look for it, you only find one alternative or the other. There is a difference. The difference is that with the light, with classical light, you would see half of the intensity on one and half of the intensity of the other. But here you always see all there or all there, but not half and half. Yeah.
I'm sorry, I don't mean to be overly technical, but 60-dimensional tomography is something I'm not familiar with. Radon at the
Sure.
century
Sure.
predicted in an analytic sense
Yep.
how you could convert that to Fourier space and then fiddle with it.
Yep.
However, we now frequently use much more sophisticated methods, and you're obviously a quote Bayesian, which
What is that quote?
Bayesian.
Oh, Bayesian. Yep.
So, are you using some sort of probabilistic schema?
That's right. So the quantum tomography that I talk about here is actually inspired and informed by the kind of classical tomography that you're discussing. So we have it's a statistical estimation theory. We have some probability for seeing a particular measurement, and then we infer, based on our priors, what we expected would have given that result. So it is a statistical, there are many approaches, but one can approach it from a Bayesian perspective, indeed. Yeah?
How has your work been used to build actual
No, it hasn't yet. But I'd say, research is hard to, the question was, how has my research helped to build an actual quantum computer? Well, we don't have one yet. I think we might begin to make some serious progress in the next decade. Probably not with cold atoms the way we envisioned. Cold atoms have been a kind of test bed. But the way research works is it's never exactly easy to say what you did that, made something happen. It's part of a more organic process whereby what you do influences the community of researchers. And I'd say, work we've done on optical lattices, on tomography and so forth has been taken up by others, and that's the best form of flattery is imitation. So there's been some, contribution within the research community, but I wouldn't pinpoint one thing that says this is going to be a quantum computer. Yeah, Terry.
Well, we have this D-wave, adiabatic quantum computing, which sort of sits in between the worlds, as I understand it. How would you describe that if it isn't quite a quantum computer?
Right. So for the camera, the question was, what about the D-wave quantum computer, which was on Time magazine's cover, somewhere in the New York Times many times. There's a company, they're out of Vancouver. They have built a machine based on superconducting technologies that is claimed to be doing some kind of quantum processing. I'd say the jury is still out. There are a lot of researchers who are trying to understand whether or not this computer is doing something different than what could be done on a big cluster classical computer. It's not working, as you said, according to the kind of logical structure that I laid out in this. It's working in a different mechanism, and it's a little hard to tease out. But I think we'll be able to tease it out. We'll be able to have a smoking gun at some point soon to determine whether or not this thing really is existing in this quantum limbo, weirdness, superposition kind of state. If I had to put my money on it and I'm on camera, I would say no. One more question back? Okay, last.
Why 16 dimensions?
Why 16 dimensions? Because we use cesium. So cesium is just the atom that's easy to laser cool because there are cheap lasers to do it with. It's one of the atoms that's in the first column of the periodic table, so it has a simple atomic structure, which makes it easy to laser cool. And it's an atom with a nucleus that has just enough so that we can stick 16 dimensions. So it's like 4 qubits, 2 friends told 2 friends to 2 friends to do 16 dimensions. And that's enough dimensions for us to do something interesting. All right. Thank you.
Well, Ivan, I'd like to present you with this citation in honor of your just tremendous scientific achievements and the contributions you've made to this university. You're a real source of pride for this university, and so thank you on behalf of it.
Thank you, Mike. Appreciate that very much. Thank you.
Just another